Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen.
Hello, good afternoon or good morning, depending on where you are. So welcome to this ATA Insights webinar on how CSP can improve grid stability, frequency stability of a power grid. So, well, today we have two experts on this subject. We have Paul Denholm from National Renewable Energy Laboratories in Colorado, in the US, and we have Julian Blanco Galvez from CIEMAT in Spain. I'll let them introduce themselves briefly, and then we'll go through the presentations. But first, I'd like to remind everybody at the audience of a kind of something we normally do at ATA Insights webinars, which is to get everybody to introduce themselves in the chat and tell us where they're joining from. So I am joining today from Berlin. So I'll stop sharing my screen and I'll get to the panelists today. So well, welcome. Paul, Julian, could you please, I'll ask you to introduce yourselves briefly in the order I see you on the screen. So I'll get Julian to introduce himself first, very briefly. So Julian, could you say a couple of, could you introduce yourself briefly, please?
Okay, thanks. I'm Julian Blanco. I'm the director of Plataforma Solar, which is a research center in the south of Spain belonging to CIEMAT. It's a public Spanish institution devoted to energy research.
Thank you, Julian, and welcome to this webinar. Paul, could you please introduce yourself briefly?
Thank you. Yes, my name is Paul Denholm. I'm an analyst at the National Renewable Energy Laboratory in Golden, Colorado in the US, and I focus on grid integration of renewable energy resources and figuring out how to maintain a stable and reliable power grid.
Thank you very much, Paul. And I think well, you'd be a known name to those who have consulted NREL's reports over the years. So, well, pleased to, I'm one of them. So yeah, pleased to meet you today. So without any further delay, if you can start sharing your screen and start your presentation.
Great. So can you see the presentation now?
Yeah, I can see it. Yeah.
Excellent. So yes, we've done some work on frequency support, frequency response of a variety of renewable energy resources, including concentrating solar power. So I'm going to go over that work briefly, but I figured it's important to start by some context about what we're talking about here. So we're talking about grid frequency today, and here in the States, it's 60 hertz, and in most of the rest of the world, it's 50 hertz. And frequency response is all about maintaining this frequency, particularly under contingency situations. So what happens when something bad happens on the grid? How can CSP or all the other resources maintain that stable frequency within the tight tolerances needed? So a real quick example of what we're talking about here. I've got a cartoon example of where you've got a supply and demand balance. And when you've got a supply demand balance, in this particular case, we've got a bunch of generators, a bunch of load. And when that supply equals demand, we have a constant stable frequency. Now, when something bad happens, so suppose all of a sudden we lose one of those big generators, well, the demand is still there. So we had 30,000 megawatts of demand or 30 gigawatts of demand. The demand doesn't know there's a loss of supply. It keeps demanding 30,000 megawatts, but all of a sudden you've only got 29,000 megawatts of supply. The question is, what happens to the grid and where does this imbalance come from? So when we talk about frequency stability, we often use pictures like this. And I don't want to go into a whole lot of detail about what's going on here, but the point is we track the frequency, we simulate and we record the frequency in real time to understand what actually happens. And what we're going to be talking about today is the first two elements of maintaining stable frequency, and that's inertia and primary frequency response. And those are the things that slow the decay in frequency and then ultimately arrest that decay in frequency. And then there's a bunch of other things that happen. Now, you may have seen a curve or a plot or something like this where you talk about all the different operating reserves and sequences of things that happen in the power grid under fault conditions or normal operation. And there's a bunch of, we talk about spinning reserves and things like that, but what we're really talking about today is the frequency responsive reserves, those pieces of the grid that actively respond to changes in frequency and measure it, monitor it, and either through inherent physics or through controls address these changes in frequency. So that's what we're going to be talking about today. So getting back to the elements of what helps maintain frequency stability, what impacts it, there's actually quite a few things. We're not going to be talking about some of these things like load inertia or the size of the contingency. We're really going to be talking about the two things that are relevant to CSP, which is generator inertia and frequency response. So basically, how much time do we have to respond to a fault? That's those first items on that list. And then how fast can we respond? And that's frequency response. So we normally have to talk about all these, but we'll be focusing on inertia and frequency response. So inertial response is as kind of a fun concept because it is physics-based. So this isn't really electrical engineering. This is literally the fact that you have kinetic energy in these rotating generators, and they will automatically inject, or really what's happening is the demand is automatically pulling electrical energy out of these generators through just physics. So this is not a computer controlled response. This is literally physical response that changes in response to frequency. So in this particular case, that 1,000 megawatt generator, it's actually generating now 1,034 megawatts because the demand is extracting 34 megawatts from that stored kinetic energy. Well, you can imagine what happens if you extract energy, kinetic energy from something. You get an imbalance and that thing will start to slow down. So that's the inertial response that happens immediately after a fault. And a big part of how much inertia a generator has is something called its inertia constant. And it varies by generator. You can imagine that as a larger generator has more inertia, but also larger generators, if they're more complicated, if there's more components to them, they have larger physical mass per unit of capacity, and they may have a larger inertia constant. Here in the States, we call it H constant. I'm not sure if that's a universal term, but that's what we call it here. But so it's basically, again, the size of the machine that that controls how much inertia it has. It's also important to note that inertia is independent of what the power plant's actually doing. So if you've got a 1,000 megawatt generator, it doesn't matter what level it's operating. As long as it's online and spinning at grid frequency, it provides the same amount of inertia response. That's a little different from all the other types of operating reserves like primary frequency response, or sometimes here in the States, we call it governor response. because of that thing, that's picture of those balls. That's a fly ball governor. And if you like old time museums like I do, you go and look at old mechanical steam equipment, you'll see a lot of these old time fly ball governors, and they literally change the settings of the valves in the plant depending on how fast that's spinning. Most of those, of course, have been replaced, but again, go to a museum and you can see these. They're kind of fun to see what these look like. So that changes the output of the power plant in response to changes in frequency, automatically increasing or decreasing its output. Now, like all other operating reserves except for inertial response, primary frequency response does require you having headroom in the system. So it means that you cannot be operating at full output, you operate at partial output, and then the governor or the controller allows you to increase or decrease output depending on the changes in frequency. Now, one of the important things, of course, is to note that there is some time it takes for these things to respond. The right is a typical curve that we use oftentimes for governor response from different types of plants. And for instance, traditional steam turbines sometimes can take quite a while to respond, a few seconds to respond to the changes in frequency. The left-hand curve is an actual measured response from an actual CSP plant. So you measure it, and then of course you do a simplified form to put in your computer model. So we have both the measured response and the actual simulated response that we then put into our models to say, okay, what happens when you get a change in frequency? That's called a step test, where you dramatically change the frequency and measure the response to the system and how long it takes, how quickly it can respond. And you can see that we're operating at partial output. So in this particular case, around 115 megawatts, we do the step test at 50 seconds. We input basically the equivalent of a drop in frequency and watch the valves open. And ultimately, you can see that the power plant increases output by about 8 megawatts to respond to that change in frequency. So we really have historically not really talked about frequency response in the power grid for the first 100 years. It's just something that we design around and nobody worried about. Nobody talked about inertia 20 years ago, but now we do. We talk about inertia quite a bit. And the reason why we talk about inertia is because wind and solar photovoltaics do not inherently provide inertia or primary frequency response. If you just put a standard old wind turbine on the grid or a standard old PV system on the grid, it provides neither inertia nor real physical inertia, nor does it inherently provide primary frequency response because they don't have traditional governors. So these curves essentially show you the amount of inertia online, and inertia is has a, it's measured in energy. But instead of like a kilowatt hour or megawatt hour, we typically talk about, at least here in the States, something called a gigawatt second, which is a funny unit, but it's still a unit of energy. But we talk about seconds because we really only need this response for a few seconds. So what you're seeing here is the left-hand curve, those lines that are flat, you're seeing the change in amount of inertia in response to the change in electricity demand. That's because we're turning on and off different power plants. And again, unlike other operating reserves, the amount of physical inertia is just dependent on the total amount of capacity online. That's why you get these changes that are basically step functions, because you're not changing, you're not gradually changing the increase, the output of individual plants to measure inertia. It's literally like, okay, I just turned on another 100 megawatt power plant, so boom, I have this kind of step change in the amount of inertia available. So during overnight hours, we turn plants off. During peak hours, we have lots of power plants on. So the inertia is highest when the demand is the highest. So that's kind of normal operation. And then when we add a bunch of wind to it, we show on the right, now the net demand for electricity is decreasing. So we're providing a bunch of energy from the wind plant. So we need less traditional thermal generators. So we decommit or turn off a lot of those generators, and you can see the total amount of inertia decreases. And that's the concern that people have. It's the decrease in the amount of inertia that results when you deploy lots of inverter-based resources like wind and solar. Now, one of the fun things, of course, is we used to worry about stability around the peak demand periods. It's really the minimum demand periods where this becomes a problem, because we're turning off all those thermal generators. If we don't do anything, if we don't increase our ability to respond to the decay in frequency that happens if you lose a large generator, you can have an event called under frequency load shedding. You can have a rapid decrease in frequency you don't have enough time for all the primary frequency response to kick in. And so the frequency can fall below these critical thresholds. And the threshold actually varies tremendously by system. And so your results will vary. But this is just one example of that event happening if we didn't do anything. And so the question is, what are we going to do? How are we going to provide the necessary response time and provide the speed of response needed to maintain frequency stability under increasing deployments of renewable energy? And there's quite a few things that we can do, but the one question is, what role can CSP provide? So CSP Provide is a traditional thermal power plant. It just uses the sun instead of coal or gas. So from that standpoint, it provides the same services as traditional generators. It provides real inertia and can also provide primary frequency response. So we have done some studies with GE here in the States to look at scenarios of reduced inertia, and specifically what happens if you replace a little bit of the photovoltaics with concentrating solar power. And so this curve is an example of one of those simulations. So the lower curve, the green, and you can kind of see some red under there, that's the case where we have just a bunch of PV in the system, and you see a decline in frequency, that rapid decline in frequency, and it falls down to what we call the frequency nadir, or the lowest frequency of just under 59.6 hertz. So that's fine. It is above the under frequency load shedding point, but it's starting to get close. And so the question is, what can you do, to prevent it falling so much? And one thing is enabling CSP governors. So in the simulation, we had a relatively small amount of the PV was replaced by PV, and this is in the western interconnection of the US. And you can see that when we had the CSP governors turned on, they helped maintain the stable frequency and increase that minimum frequency. You can kind of see just the inertial response in the red. It wasn't a huge impact, but the combination of those two things helps. But it was primarily the governor response in this particular case. There's a few other things that you can do in cases where you're getting to larger deployments of renewable energy. One of them is you could make CSP respond faster. So we did simulations of units that were designed to have more faster response from an event like this. So you can see here the change in output from a CSP plant with and without this fast response. So the red curve has that faster response and increases output more rapidly to, again, provide greater response to a decline in frequency. So there are a bunch of important caveats here. One of the issues, of course, is that outside of Texas in the U.S., this is actually not a market product, which means you can't get paid for it. So you'd have to make sure that your power purchase agreement or your local utility appropriately values the provision of this response from a CSP plant, because again, there's not a market for it. And the other thing, of course, is I don't think this is the savior of CSP, right? There's a lot of concerns in the CSP industry with the declining costs of PV and batteries that CSP will, it's going to be a challenge. And I do get a lot of calls and discussions. Okay, is this the thing that will make CSP critical? Is this the thing that will tip the edge? And we have to be really careful here. There is value here, there's no doubt, and it can add to the value of a CSP plant, but the total amount of these services needed in the grid, especially in large grids like the US, is relatively small compared to the overall size of the grid. And if you've got hydroelectric plants and other renewable resources that can provide these services via synchronous generators such as geothermal, they're going to compete against you. But I think the biggest challenge, of course, is that wind, solar, and batteries themselves can provide alternatives to traditional physical inertia and traditional primary frequency response, particularly because they can react so fast and provide something called fast frequency response. And we have done a bunch of simulations where if you enable fast frequency response from wind, from solar, it can provide a substitute for traditional physical inertia, and kind of, again, digs into that opportunity for CSP. So There definitely is an opportunity here, but I wouldn't say that we've found that, okay, CSP has to be deployed because there are alternatives. It is an increase in value, so that's something to keep in mind. But again, there are alternatives, so we do have to be careful about overstating the critical nature of CSP in providing these resources. So I think there are definitely opportunities here. We should definitely look at them and also consider how CSP plants might be modified slightly. We're not talking about massive changes here, right? Because again, the relative value of these services is not huge. So we can't spend huge amounts of money making changes to our plants to provide these. But there may be small changes to the mechanical side of the plant that could increase its value by providing more of these services or at a faster rate. So that's something to keep in mind. And of course, it highly depends on your local utility. And that's what I have to say about that. And happy to take questions at the end after we hear from our next speaker. Thanks.
Great, thank you very much, Paul, for your presentation. So, yeah, I think as Paul said, he'll be happy to answer questions. So send them through the Q&A box, which you'll find at the bottom of the screen. So, Julian, whenever you are ready to start presenting, please share your slides and just get started, please.
Okay, is this okay? It's fine?
Yeah, I can see it, yeah.
Good. I'm going to discuss this topic in a wider context. So I'm going to present one study has been recently performed about the potential role of CSP in Portugal. I mean, this study, this work has been done by ProThermoSolar, which is the Spanish Association of Concentrated Power Industry, together with CIEMAT, which are the one that we belong. First of all, I want to briefly I briefly introduce my center. I'm the director of Plataforma Solar, which is a center located in southern Spain devoted to CSP, and Chair 1. We belong to CIEMAT, as I said before, and Plataforma Solar is one of the biggest centers in the world devoted to the research of CSP technology and its application. We have a very large portfolio of research facilities dealing with all the technologies and also all the application. And we have recently achieved the 40-year of existence in that. And we are addressing a very large number of research covering all the spectrum of topics and technologies of this. In this center, we have developed one tool that has been used for this study that has been made in Portugal. This is the main figure of the National Energy Plan, Climate Plan of Portugal, which submitted to the European Commission, which said that about 60% by 2030 to 50% of the input will be made by renewables, basically solar and wind.
Julian, I don't know whether you can hear Julian, Paul, but I've lost him. So
Sorry?
is it? I lost you for a second there, Julian. So.
Oh, I'm very sorry. I mean, it's just to you lost my voice, or you lost?
Yeah, your voice. Yeah, your voice and your video was frozen.
Okay, I'm sorry. I said that this is the basic figure for the National Plan, Climate Plan, Energy and Climate Plan of Portugal, submitted to the European Commission. And the goal for 2030 is that to have 60% of the contribution from solar and PV, 80% total renewable input, 55% of CO2 emission reduction. And what it is a schedule of CSP participation is about 300 mega by this year. The expected capacity in Portugal by 2030 is the one that it is shown here. Basically, the main data is that the coal is expected to completely abandon, to reduce, and the natural gas will be maintained in combined cycles as it is, and all others will increase the renewables basically to cover the expected demand increase. There are some typical ideas is that one of them is that the curtailment is not expected to be an issue as the batteries and hydrogen will absorb, and also that the natural gas cycle will be the answer when PV or wind are not producing. But what it is true is that there is a number of questions that all the policymakers address regarding to the high penetration of renewables in the system. It's about the exporting, importing, is about the capacity to meet the demand, is about the dealing with the high level of curtailments, etc. And this is to address all this is that we have developed a specific tool that is based on inductive project planning, based on artificial intelligence, which try to address in a specific mix what are the optimum combination of different sources to provide the minimum cost or the specific boundary condition that could be imposed. The starting point that we start is the real year with the actual demand and generation of the data. We complement with the specific profile of PV and CSP that historically is available in that country. We have one specific number of inputs as the planet installed capacity, the target of CO2 emission, in demand increase, the cost of all the sources, the CO2 emission, etc. And the model that has been developed minimize curtailment and the curtailments and provide a number of solution, valid solution, and discarding many of them, that in all of them we achieve the output is the pair that is given by the cost and the number of curtailment that this mix produce. I mean, in addition, other relevant outputs are the synchronous power, natural gas ramps, and all the imported and exported energy. This is the scheme, general scheme. I'm not going to enter, but it is important that we take into consideration all the curtailment costs, all the export and imports needed in any moment, all the solution that does not met the target, met the requirement that is imposed are discarded, and all the valid solutions are, let's say, taken just to, and also try to minimize the curtailments, just to reduce all the non-dispatchable sources, just to address this. This is okay. Just to also we have to start with a number of performance assumptions. One of them is that in Portugal, just as hydro is significant, is highly representative because there's a lot of power of hydro. We were asked to consider both cases, like some kind of sunny and dry and wet scenarios. Yes. So from the historical, let's say, data we selected 2 years. One of them, 2019, is representative of the sunny years, and 2018 more representative of rainy and wet year. Additionally, We started by the total installed power that is done today in Portugal. One expected demand increase, we consider 1.5% up to 2003. Total CO2, let's say, emission of the different technologies, basically coal and natural gas and cogeneration, also adjusted to the specific amount of gas that is expected to be affected by the strong penetration of renewables. The storage, basically all the hydro that it is significant, pumped hydropower, and solar thermal. And in this way, the solar thermal is considered to have high number of storage hours for the thermal storage, 12 hours. Also, we have to consider the cost of the different technologies. This is the table that show the data considered. The specific cost of wind, PV, and solar and CSP was based on the specific recent auction in Spain and Portugal, and the recent also lending curve and but also the industry. Several companies indicated that was expected up to 2030 year. Additionally, we have to consider that the possibility that one specific technology in this context does not achieve the minimum number of hours of operation. In this case, this minimum hour is the one that we consider just to assume that this cost of the previous table is allocated. So for one technology, just to achieve this cost, that means a minimum number of operation. If that minimum hours is not achieved, the associated cost is also considered. And also the curtailments has a cost that has been to add to the system. So in order to be fair, to have the overall cost of the system could be really relevant to the whole grid. Okay, this is the results that we achieved. So we have a huge number of points that are, all of them are suitable and that are according to the specific condition imposed. So all this is, each point is a mix, specific different mix of all the previous technologies, but specifically that we are looking for, where we have more interest, is the contribution of PV, wind, and CSP, and this has been made also in dry and wet years. Okay. On the vertical, we have the cost. On the horizontal axis, the curtailments. You can see if we go to the right, this means that we have high representation of intermittent renewables or intermittent sources. And if we go to the left, we have the higher percentage of dispatchable resources. What we are especially interested is in the Pareto front, which is the number of solutions which are in this line, that it is just has the minimum level of both cost and curtailment, because this has of course the optimal solution to us. So when we address this, we have this specific results. All this tool is providing information about what are the range of combination that, from the policy point of view, meet all the imposed requirement, CO2 emission, etc. And all of them give us a specific mix of technologies. More specifically, that I say with this, we are interested in this region, which is the one that is relevant to us. You can see here the green point is the one of the national plan, is providing cost of 3.95 euro cents, and this is with a specific mix of technologies. This is the one that officially are scheduled to have in 2030. But the one that is in yellow is shown here is one that has having the same cost provide 35 less curtailment than the previous one. And the difference is that in the first one we have 30 mega of CSP, and in that one we have 550. Other solutions provide also that are in the Pareto front, provide also valid solution, and you can see that how with very minor cost increase, you can see in the case 3 we have just 4% of the cost against the previous one, but the curtailments reduce 50%, and that way the 4 case the increases and the cost is 7%, and the curtailments 56%, and in the final one, just with 10% of cost increase, we have 60% of reducing the curtailments. We are addressing all this, and then we achieve that. I mean, this is the case of the wet years. We can recommend, or the study recommend, a range around 1.5 giga of CSP in Portugal, which could provide, let's say, cost increase in the overall electricity around between 4 to 7% with regard to the reference that we achieve with the specific target, national targets. But also we can this reduce the increase of the cost can provide significant reducing the curtailments, more than 50% with regard to the official plan, but also a significant improvement in the total amount of synchronous power that it is produced. I will back to this later on. In the case of the sunny year, the reductions are quite similar. We have just very minor cost increase with even higher significant reduction on the curtailments. So if the installed capacity would be 2 giga, this will reduce the curtailments up to 80%. And this is could also provide us increase of the synchronous power, and also is not affected practically the amount of imported energy that will need the country. You can see here in what is the evolution of the curtailments against the CSP capacity that could be introduced in the system. You can see that in the sunny year we could have from 0.3, which is the starting point, up to close to 2. We can see that the curtailment could be reduced in the range of 1.5 giga, around 75%, around always against the reference of the national plan. In wet year, we have for the same amount, 1.5, we will have 50% of curtailment reducing. And what about the synchronous power? So you can see that from the country, there are 2 reference. One of the continuous line is the total amount, I mean, with regard to the reference of less than 1 giga of conventional of synchronous power connected to the grid. The dot is less than 500 mega. You can see how in the case of sunny years, the introduction of 1.5 giga of CSP could reduce the total amount of the time that could be below this level, more than 60%. And in the case of the wet year, we could be around 50%, 60% on that, all of this. So this is significant, let's say, increase on the total amount of the risk of being below this threshold defined by the government. At the end, the key message is that the CSP can provide in significant portion of the year the role that now can have the hydro, just to replace the necessity of the gas-fired combined cycle plants in significant portion of the year. This is just to, with all the same comment that we made before, just to. So just to go with some conclusion, because you can see the study is much wider than I try just to summarize the key points. But the conclusion is that this is an automatic method just to define an optimum mix of energy, mix in a specific country, region of context, also providing the possibility to additional weighting criteria of policymakers. I forgot before to say that all this procedure was initially developed by Proterma Solar, and we did at CIEMAT is just to make some automatization, introducing some kind of automatic procedure and artificial intelligence just to address all the process. We have performed the study in Portugal, and it has been recommended a range between 1.2 and 2 giga of installed CSP power over the actual figure of 0.3 giga. And this solution can reduce the curtailment between 50 and 80%, also providing a significant increase in the synchronous power, also with all of that with very little or very minor variation in the total cost of the system. In Portugal, CSP can displace natural gas contribution and also complementing hydro on dry years. And this complementarity of hydro and CSP, I think that we consider this one of the best strategy in the specific case of Portugal, with very high potential of hydro. Also, lower curtailments could motivate, we think that could motivate the future investment in commercial projects. But this reduce significantly the curtailment. This could also reduce uncertainties on projects starting up to after a specific threshold. In addition, we should remind that the storage system of CSP could provide an independent infrastructure that could deliver full nominal power at peaking demands in a specific context. Just to also notice that the Portugal renewable target for 2030 is 80%. However, the CSP benefits substantially increase when we goes beyond this figure. We have up 80, 19, or even higher share of renewable penetration. And here, when we see that this benefit of CSP appear more substantially and much more clearly due to the lack of dispatchable renewable sources that in this context. We have addressed similar or very similar study in Portugal, and the result in Spain, and the result also are quite similar. And that's all. I hope that this could be of interest for the audience.
Thank you very much, Julian, for your presentation. I think I'm sure there will be questions about the assumptions and all of that. So if you have the link at hand, it would be good if you could share it in the chat. I think some people would appreciate it. So let's start with some of the questions. So I have here a question for Paul. So what types of power grids would benefit the most from CSP providing frequency response?
Yeah, so one of the things, of course, is the competition from other resources. So when we have done our simulations, if there are scenarios where you don't have hydro, if you're trying to decarbonize, obviously a lot of this depends on on the amount of decarbonization you're trying to do. Situations where you don't have hydro or geothermal or some of the other renewable resources that have synchronous machines, those are potentially advantageous to CSP. So it really is system dependent, and you kind of have to look at the system. One of the interesting things that we often get is the role of nuclear power, for instance. And I like to point out that in here in the U.S., nuclear power and frequency response is a problem, not a solution. It is the nuclear power plants themselves that drive the frequency response obligation. So places like Texas have large nuclear power plants that are the cause of the frequency response problem, and Texas doesn't have a whole lot of hydro, so there could be opportunities in Texas. It would be a place where I would particularly be interested in looking at its ability to provide frequency response here in the States. So it does depend on the other kind of mix of resources to find those that are best for CSP.
Mm-hmm. Thank you, Paul. And Julian, I don't know if you'd like to add to these questions. So the question is, what types of power grids would benefit the most from CSP providing a frequency response?
So clearly the ones in which the penetration of non-dispatchable, especially PV and wind, are really very high. However, I mean, from our estimation, the penetration of renewable this is starting just to be challenging to the current system when we are just beyond the range. It depends on the context of the different countries, but beyond the 70–80% of renewable penetration, this could be challenging. It could be let's say a problem, because just from the safety point of view, there are many countries that define, okay, I need just to have at least this amount of conventional synchronous power that's providing energy to the, and this is really significant, at least from the case in Spain. I don't know many countries that try to be conservative on this.
Yeah, well, I think, related question is on the other services that CSP could provide other than frequency support. I think Paul mentioned that these would be so to say another string on CSP's bow, but not the main reason for deploying CSP. So what other services could CSP provide to the grid other than frequency support? I don't know if you'd like to start, Paul.
Sure. So again, CSP can pretty much provide any service that a regular power plant can. If it's got thermal storage, it can do. Obviously, its main provision, its main value is providing capacity and energy, and that's very important. Capacity in particular. I think we all have to recognize the fact that with sufficient energy storage, particularly in summer peaking systems, CSP is a really good source of firm capacity. So that's critical that be appropriately valued. But on top of that, you do have these other services in the U.S. Regulating reserves and spinning contingency reserves are both compensated service in every single market region in the U.S. And so CSP can provide those services. And it can do just as well as any other thermal plant. So it's got all that flexibility. Obviously we have to always be careful that how much of that service is needed, what are the competitors, but CSP can absolutely bid into those markets and get additional revenue for those services.
Thank you, Paul. And Julian, what's your experience, in the markets you have seen?
I just came to my mind a couple of the results from this study in Portugal. We observed that in the year 2030, the inclusion of 1 giga of CSP could reduce, the total installation of PV and wind just by around 3 giga. So in order just to have the same amount of energy into the system. So the dispatchability that provide the CSP, I mean, we're considering large amount of storage. Yes, I mean, you have higher installation costs, but we also avoid the installation of a significant amount of non-renewables, just to have the same, let's say, portfolio of the same performance. And also this means that all these non-dispatchable that we reduce, I mean, we can also permit or just to increase this amount of non-dispatchable renewables. So this is just both items that I think are highly positive just to the system.
So bottom line is that with CSP you can incorporate more variable renewables into the grid. Right.
Yeah. Right.
And I think
and to the same grid performance, just to one specific amount of CSP is equal to around 3 times non-variable renewables. In this case, PV and wind. Yeah.
And I think if I remember correctly, that I've seen an NREL report that looks into this. So what have you seen in the US, Paul? Could like CSP help incorporate more variable renewables in the grid over there as well?
Yeah, so we've seen this as well, and that's a fantastic topic to talk about. CSP plants designed appropriately flexibly, and for the most case they are, they can reduce the reliance on must-run thermal plants with what we call high minimum stable levels or high minimum generation levels. So particularly coal plants, you can only turn them down so much before you start having stability issues. And CSP can typically provide a little bit more flexibility, or in some cases a lot more flexibility in those plants in terms of minimum turn down ratios and things like that. So you can absolutely have cases where if you replace a fossil plant with something like a CSP plant, you get more overall flexibility to integrate more variable renewables. So yeah, there is a nice synergy there.
There is another factor that is specifically interesting in the case of the Iberian Peninsula. The Iberian Peninsula has very limited number of interconnection with other countries. It's not the case of Germany, for instance. And this means that it is could be one of the reasons why the grid authorities are used to be highly conservative with regard to the total amount of minimum synchronous power that they define into the planning, to say. And this is why the Spain and Portugal is a very interesting example how to deal with this very high penetration of renewables expected that we're going to happen the next year, and how this could be a problem or not from the point of view of the stability of the grid and the frequency problem. Just to, this is specifically why the CSP can provide some kind of additional benefit from the safety point of view to guarantee that this minimum that is defined by authorities could always be achieved, will be present, even in the case of very high penetration of renewables, non-dispatchable renewables.
Thank you. And there is an interesting question here, which is by Danny Q, who if it is who I think it is, he knows what CSP plans are about, and is asking what's the behavior in terms of frequency response of a thermal TS plus PV hybrid plant. I suppose that would be a PV hybrid plant with thermal storage. With thermal storage. So either have you looked into this in your studies? It can a PV plant with a thermal storage system provide these types of services as well?
The short answer is yes. I mean, it's really just an optimization question, and it's challenging to kind of put this in the solution space. But yeah, I look forward to getting a better understanding of what these systems can do.
We expect to have the first plant in Spain soon with this, and from the commercial point of view, it's clear that all the future projects will be hybrid PV and CSP. And we have to see some plants, what is the amount of PV, and what it could be the real impact on the performance from the grid point of view.
Right. So we just need to see a few more of these connected to actually see how, to what extent they could perform these services, and how they could contribute to the grid as well. And I think you touched upon the point of CSP PV hybrids as well now, and there is a question by Amanda Granis here, and she asks, do you see hybrid solutions of both CSP and PV as more viable compared to purely CSP? So, in your answer, you mentioned, well, we think that we'll see more CSP PV hybrids. Why is that?
Sorry, I missed.
So, why? So you mentioned that we'll see more CSP plus PV hybrid plants. So why are they a good combination?
Yes, they are cost effective. This is just the basic idea is just to provide, let's say, together with, if needed, a small amount of power from CSP during the day, the sunny hours, to provide the energy, the power basically by the PV, but thanks to the thermal storage to provide the rest of the energy during the night and the peak time that the energy is needed.
Okay.
We have to see what is the best the best time and the best allocation of the CSP, or the optimal allocation in the energy grids, according to the reduction of the different evolution of the different mix in the future.
So that's a really interesting question, and just to follow up on that, I mean, one of the really interesting things about CSP is we often think about levelized cost of energy, and obviously there's all kinds of problems with that as a performance metric. But one of the interesting things when you look at the levelized cost of energy of the fraction of energy stored, right? So think about a PV plant without storage versus a CSP plant without storage. Now we all know that PV is going to beat out the CSP plant. If you need to store a little bit of that energy, you're still going to do PV plus batteries. But as you increase the fraction of the energy that you need to store, the slope of the lines of the LCOE curve. So if you think about cost of energy on the y-axis and the fraction of energy stored on the x-axis, the CSP plant, the slope of that line is fairly shallow, right? I mean, thermal storage component is fairly cheap, whereas the slope on the PV plant is high. And so the question that I think is critical is, where do the slopes of those two curves intercept? And I think, I hope that, if we want there to be a future of CSP, there'll be a place where, like, okay, you've saturated the daytime demand with PV, and you need to still provide energy at night. If most of the additional solar energy that you need is needed at night, that's the place where that CSP plant becomes cost effective. And then, of course, adding on top of that all these additional value streams. So that's the way that I kind of like to think about the surface space of the PV plus CSP hybrid. At what point does the storage element of CSP become more cost effective? So something to think about.
Right. I think, well, I remember a study that was quoted that I think, if I remember correctly now, that it was less than 4 hours you would use PV plus batteries. More than that, you would use like CSP plus thermal energy storage would become more cost competitive. But yeah, but it'd be good to see, you know, a new revised edition of that study to see how they would behave with today's prices. So well, we're coming up to the end of the webinar. All good things, this webinar must also end. So you know, I'd like to thank everybody who connected today to watch presentations by Paul and by Julian. I think we've all learned a lot today. Yeah, so thank you, Paul. Thank you, Julian. I don't know if you have any parting words for the audience before we leave.
No, just to thank you for the opportunity, and just to keep on contact with if anybody has any question of just want to consult, we are more than welcome to receive any input, and we will try to provide answer to anybody.
Thank you very much, Julian. Paul, any parting words?
Just to thank you for this opportunity. I always love talking about frequency and CSP, so it's a fun topic, and keep on getting those technologies deployed.
Brilliant. Well, thank you very much, and yeah, just like to remind everybody that yes, we have recorded this webinar. You will get an email with a link to the video recording and the slides. And thank you for being with us today. I hope that to see you here next time as well. Until next time, bye.
Wow.
Thank you. Bye.